So next up we have Míriam Febrer. She's joining us from Spain, from Barcelona. She's not a Barcelona fan though. But her brother is, so she gets all the updates.
Annie was wrong. It contributed 1 centimeter in the front, but about a half a foot size in the back, which is a lot. It's like 50% of your foot. It's a lot.
Okay, yeah. Hi, good afternoon. I'm Míriam. I'm a PhD student at UPC Barcelona, and I will talk about this active orthosis that we have developed and how we are trying to personalize it to each patient using optimal control simulations. So with other 2 labs in Spain, we have developed this knee ankle foot orthosis that is intended for spinal cord injured subjects that have no mobility at knee and ankle level, but remain some hip function. So these patients are able to walk with passive braces and crutches, but this type of walking is very exhausting for them, so they usually use wheelchairs. Our idea is to use these passive supports and add a motor at the knee and a sensor at the shank to detect gait events, and all the electronics and power supply go inside a backpack. So during stance, the motor is locked, and during swing, it actuates the knee following a predefined knee angle trajectory that can be adjusted modifying the values of these parameters. And the patient is the one that decides when to initiate each step by raising a little bit his hip. What we are doing now is to adjust these parameters manually, and our idea is to use subject-specific simulations to find the optimal values for each patient. So what I am talking today is the first step toward this long-term goal. First, I will explain this model that we have developed of an SCI patient, and also the optimal control framework that we are using to track an experimental motion and at the same time reduce the residual range acting at the pelvis. We have collected marker data, foot ground and crutch ground reaction forces of this patient walking with passive orthosis, and we have developed a model in OpenSim based on an available model. We have scaled it to the subject, added the orthosis and the crutches rigidly attached to the corresponding segments, and the model has 29 degrees of freedom that correspond to the absolute position and orientation of the pelvis and all the other relative joint angles. The tracking problem is formulated as an optimal control problem, where the states are coordinates, velocities, and accelerations, and controls are jerks. The experimental data is used as an initial guess, and in the cost function we minimize the squared error of the coordinates and the square of jerks, and at each iteration we perform an inverse dynamics using OpenSim API, and we put the residuals into path constraints where we ask them to be within a specific tolerance. And since we are using the experimental values of the ground reaction forces, we need to be sure that the feet and the crutches touch the ground in the time and position corresponding to the experimental data. So we do that adding additional constraints where we track this position of some markers at the feet and the crutches. The problem is solved using the direct collocation solver GPOPS2, and it finds the optimal solution in around 25 minutes. Here we have some results. We can see for each component of the residual range the root mean square before and after optimization, and we can see that it has been reduced more than 85% each component. If we look at the coordinates, we can see that they are slightly modified in order to achieve this reduction of the residual. And for the angular coordinates, the mean of the root mean square error is between 4 and 5 degrees, and for the linear coordinates is between 2 and 3 centimeters. What we are doing now is to develop and calibrate a foot ground and crutch ground contact model using this same framework, but instead of using the experimental ground reaction forces, we compute them using compliant models. And in the cost function, we add a new term that minimizes the square error of the ground reaction forces. And when this is done, our next step will be to add the knee actuation to this framework and see how to model each one of these parameters of the knee angle trajectory that are the ones that we want to optimize for each patient. Thank you very much for your attention.
All right, questions for Míriam?
Maybe I just missed it, but how did the modeling and optimization framework cause the muscle behavior in the human part of the model to adapt?
We don't have muscles in this model.
So, forgive me, what was the OpenSim model doing? I think I must have missed it then.
Okay, so the OpenSim model, we are using it at the skeletal level. I mean, we solve the inverse kinematics and dynamics, but we stay at the torque level of each joint.
So you're using it as a model of basically transmitting the torque and power source from your exoskeleton through the skeletal model to the world. Is that true?
Okay, so now, at this stage of the work, we are not modeling the actuation of the orthoses. So now we are assuming that the orthosis is rigidly attached to the patient. And then since the patient cannot do anything at the knee and ankle level, we assume that all the torque at the knee comes from the motor, but we are not modeling the dynamic actuation of the motor at this moment.
Okay, thank you.
So really briefly and kind of at a high level, would you mind talking us through kind of the advantages of going about this optimization in a simulation setting versus kind of having a session and working with the subjects experimentally?
Yeah, so for the patient, when we are using the trial and error approach with the engineer or the doctor that is modifying these parameters values. So for the patient, it's a little bit like an exhausting process. And also when you find a combination that works correctly or that seems to work correctly, you don't know if it's because you are tired of trying or it's the optimal for that patient or not. We don't know if we will achieve, if it is difficult to do this also using optimization or prediction, but we want to try that because we think that maybe it will be easier and more quickly to implement, and for the patient also it will be better.
You said the motor keeps the knee locked. Do you mean there is a clutch and motor actuates the clutch, so the knee is locked, or motor generates a torque opposite to knee flexion, so the knee remains locked?
Okay, no. It's locked with the clutch during stance, and then during swing it actuates the knee.
Can it unlock under load when the human is in stance?
Can you repeat? Sorry.
When the patient is in stance and the knees are locked, is the motor strong enough to unlock the knee? And then how much does it weigh? Okay,
so the things that, I don't know with much detail about the functioning of the motor. So yeah, but if you are interested, I can, we can talk later and I can.
Thank you, Míriam.
Okay.